Hello students. Welcome to Swami Vivekananda Group of Institutes, the official YouTube channel of Sri Ramakrishna Institute of Science and Technology and Swami Vivekananda Institute of Science and Technology. In today's video, we will solve the numerical of the chapter Physical World, Units and Measurements. This is the first unit of the subject Applied Physics 1 under the Diploma course in first year, first semester. For your convenience, I will divide while discussing the numerical of this chapter in two videos. In this video, I will solve the numerical related to the dimensional analysis of physical quantities. So, without any further delay, let's jump into the discussion. In our first problem, we need to find out the dimensional formulae of three different physical quantities, namely, universal gravitational constant, surface energy, and Young's modulus. To determine the dimensional formula of universal gravitational constant, we will refer the Newton's law of gravitation. According to this law, the force between 2-point masses m1 and m2, separated by a distance r, is given as F is equal to capital G times m1 m2 divided by r square. Capital G is a proportionality constant and is known as universal gravitational constant. From this equation, we get the expression of G as G equals F times r square divided by m1 m2. We will be using this relation to find the dimensional formula of universal gravitational constant later. Let us find now the dimensional formula of force, F. We know that force is equal to mass times acceleration. The dimensional formula of mass is capital M within square bracket, and dimensional formula of acceleration is capital L, capital T to the power minus 2 within square bracket. So, the dimensional formula of force, F is capital M, capital L, capital T, to the power minus 2, within square bracket. Now, the dimensional formula of universal gravitational constant can be obtained by substituting the dimensional formula of each quantity in the expression of G and simplifying the equation. Hence, we obtain the dimensional formula of universal gravitational constant as capital M to the power minus 1, capital L to the power 3, capital T to the power minus 2 within square bracket. In the second part of our first problem, we need to find out the dimensional formula of surface energy. According to the definition, the surface energy is the potential energy of the surface molecules per unit area of the free surface of the liquid. So, surface energy is mathematically expressed as energy divided by area. We know that the dimensional formula of energy and work is the same. Work is force times displacement. So, the dimensional formula of energy is capital M, capital L square, capital T to the power minus 2 within square bracket. Now, the dimensional formula of area is capital L square within the square bracket. So, the dimensional formula of surface energy can be obtained by substituting the dimensional formula of energy and area in the expression of surface energy and simplifying the expression. Hence, the dimensional formula of surface energy is capital M, capital T to the power minus 2 within square bracket. In the final part of our first problem, we need to find out the dimensional formula of Young's modulus. What is Young's modulus? Within elastic limit, the ratio of longitudinal stress to the longitudinal strain is called the Young's modulus. So mathematically, Young's modulus is equal to longitudinal stress divided by longitudinal strain. Let us now know what is stress. The internal restoring force acting per unit area of cross-section of a deformed body is called stress. So mathematically, stress is equal to force divided by area. Substituting the dimensional formulae of force and area, we obtain the dimensional formula of stress as capital M, capital L to the power minus 1, capital T to the power minus 2 within square bracket. Strain is measured by the ratio of change in configuration to the original configuration of the body. So, it is a ratio of two similar quantities and hence dimensionless. Hence, the dimensional formula of Young's modulus is exactly the same as that of the stress and is given as capital M, capital L to the power minus 1, capital T to the power minus 2 within the square bracket. In our second problem, we are asked to convert the value of universal gravitational constant from CGS systems of units to SI system of units. This problem is based on the application of dimensional analysis, in which we convert a physical quantity from one system to another. The standard dimensional formula of a physical quantity can be written as capital M to the power A, capital L to the power B, capital T to the power C within the square bracket. The formula, which I am going to use to solve this problem, is given below. Here N1 and N2 are the two numerical values of the same physical quantity, which is the universal gravitational constant for this problem, in two different system of units. I will be using suffix 1 for the first system of units, which is the CGS system of units for the given problem, and the suffix 2 for the second system of units, which is the SI system of units. We know that the dimensional formula of universal gravitational constant is capital M to the power minus 1, capital L to the power 3, capital T to the power minus 2. Now, comparing this dimensional formula of capital G with the standard dimensional formula of a physical quantity, we obtain A is equal to minus 1, B is equal to 3 and C is equal to minus 2. Let us now write the values of N, capital M, capital L and capital T in CGS system. Here, N1 is equal to 6.67 into 10 to the power minus 8. Capital M1 is equal to 1 gram. Capital L1 is equal to 1 centimeter. Capital T1 is equal to 1 second. Now, we will consider the same quantities in terms of the second system of units, which is the SI system. Here, N2 is unknown, as we have to find out this value. Capital M2 is equal to 1 kilogram, which is equal to 10 to the power 3 grams. Capital L2 is equal to 1 meter, which is equal to 10 to the power 2 centimeters, and capital T2, which remains the same in all system of units and is equal to 1 second. Substituting all these values in our reference formula, we get the following expression. Now, simplifying the above expression, we find that N2 is equal to 6.67 into 10 to the power minus 8 multiplied by 10 to the power 3 multiplied by 10 to the power minus 6 multiplied by 1. So, finally, we find the value of N2 as 6.67 into 10 to the power minus 11. Hence, the universal gravitational constant in SI system is 6.67 into 10 to the power minus 11 meter cube, kilogram to the power minus 1, second to the power minus 2. In our third problem, we have to check the dimensional correctness of a given relation. This is another application of the dimensional analysis. In this problem, the given relation relates three physical quantities: the torque acting on a body, the moment of inertia, and angular acceleration of the body. The relation is tau is equal to I, alpha. Remember, torque, denoted by tau, is the rotational analog of force acting on a body. It is measured by the product of the magnitude of the applied force and perpendicular distance of the line of action of the force and point of rotation of the body. So, torque is mathematically expressed as the product of force and distance. Therefore, dimensional formula of torque is capital M, capital L square, capital T, to the power minus 2, within square bracket. This is also the dimensional formula of work. But remember, torque and work are two different physical quantities. Next is the quantity, moment of inertia, denoted by I. Mathematically, moment of inertia is expressed by the product of mass of the body and square of the distance. So, the dimensional formula of moment of inertia is capital M, capital L square within square bracket. Finally, we have angular acceleration denoted by alpha. Angular acceleration of a body is the time rate of change of angular velocity. Again, angular velocity is the time rate of change of angular displacement. So, mathematically we can express the angular acceleration as angular displacement divided by time square. Angular displacement, or angle, is a dimensionless quantity. Therefore, the dimensional formula of angular acceleration is capital T to the power minus 2 within square bracket. Let us now find out the dimensional formula of the right-hand side of the given equation. The dimensional formula of I alpha can be obtained by substituting the dimensional formulae of I and alpha. Hence, we obtain the dimensional formula of the right-hand side of the equation as capital M, capital L square, capital T to the power minus 2 within square bracket. This is exactly equal to the dimensional formula of torque. Therefore, we can say the dimensional formulae of left-hand side of the equation and that of the right-hand side of the equation are the same. So, the given physical relation is dimensionally correct. In our fourth problem, the dependence of the frequency, denoted by small f, of a stretched string on three physical quantities, are given. We need to relate f with these quantities. This is the final application of the dimensional analysis in which we derive a relation among the given physical quantities. The physical quantities cited in the problem are tension in the string, denoted by capital T, length of the string, denoted by small l, and mass per unit length of the string, denoted by small m. Let us consider that the frequency depends on the tension raised to the power a, length of the string raised to the power b, and mass per unit length raised to the power c. So, mathematically we write small f proportional to capital T to the power a, small l to the power b, small m to the power c. When we replace the proportionality sign by an equal sign, we introduce a proportionality constant. So, we write small f is equal to small k, a proportionality constant, times capital T to the power a, small l to the power b, small m to the power c. Now, we will write the dimensional formula of each physical quantity of the equation. Frequency is the number of complete oscillations per unit time. It is mathematically expressed as the reciprocal of time period. So, the dimensional formula of frequency is capital T to the power minus 1 within square bracket. In terms of m, l, t, we can write the dimensional formula of frequency as capital M to the power 0, capital L to the power 0, capital T to the power minus 1 within square bracket. Next is tension, which is nothing but force. Hence, the dimensional formula of tension is capital M, capital L, capital T to the power minus 2 within square bracket. Next is length, which has the dimensional formula capital L within square bracket. Finally, the mass per unit length is mathematically expressed as mass divided by length. So, the dimensional formula of mass per unit length is capital M, capital L to the power minus 1 within square bracket. Now we will write the reference equation in terms of dimensional formulae of the quantities. Equating the powers of m, l, and t on both sides of the equation, we get the following three equations. A plus c is equal to 0. A plus b minus c is equal to 0. And minus 2a is equal to minus 1. Solving the above three equations, we get a is equal to half, c is equal to minus half, and b is equal to minus 1. Hence, substituting these values in the equation, we get small f is equal to small k, capital T to the power half, small l to the power minus 1, small m to the power minus half. Therefore, small f is equal to small k divided by small l times under square root capital T divided by small m. The value of k is found to be half experimentally. Hence, the final form of the physical relation becomes small f is equal to 1 by 2L under square root capital T divided by small m. In our fifth and final problem of this segment, we need to find out the dimensional formula of small a divided by small b from a given relation where both small a and small b are constants. This problem is based on the principle of homogeneity of dimensions, or simply dimensional homogeneity. According to the principle, a physical relation or equation is dimensionally correct if the dimensions of fundamental quantities are the same in each and every term on either side of the relation or equation. This principle is actually based on the fact that we can only add or subtract those physical quantities which have the same dimensional formulae. The given relation is capital F is equal to small a root x plus bt square, where F denotes force, x denotes distance, and t denotes time. Since the given relation is dimensionally correct, each term on the right-hand side of the equation must be equal to the dimensional formula of force. So, the dimensional formula of the quantity a root x is equal to that of force. Therefore, the dimensional formula of small a is equal to the dimensional formula of force divided by the dimensional formula of root x. Substituting the dimensional formulae of force and length, we get the dimensional formula of a capital M, capital L, to the power half, capital T, to the power minus 2, within square bracket. Similarly, the dimensional formula of bt square is also equal to that of force. So, the dimensional formula of small b is equal to the dimensional formula of force divided by the dimensional formula of t square. After substituting the dimensional formula of force and time and simplifying, we get the dimensional formula of b capital M, capital L, capital T, to the power minus 4, within square bracket. Hence, the dimensional formula of small a divided by small b is capital M to the power 0, capital L to the power minus half, capital T square, within square bracket. So students, this concludes our today's video. In our next video, we will solve the numerical related to significant figures and various types of error calculations of this chapter. Till then, practice the types of numerical that I have discussed in this video.